In high-speed digital circuit design, moving data is like a high-speed race. If signals arrive a fraction of a second too early or too late, the data collides and the entire system crashes. This schematic shows our specific problem. We need to calculate exactly how much timing variance this circuit can handle while running at a strict 2 GHz clock frequency. To guarantee the system stays stable, we have to find the upper and lower limits of that variance, known as clock skew. We need the maximum and minimum tolerances before the timing breaks. Let's break down the math. At its core, data travels from a launch point to a capture point. The exact moment it is allowed to enter that destination is controlled by a clock signal, acting like a traffic light. This diagram shows positive clock skew. The capture clock triggers later than the launch clock. Because the clock source sits closer to the launch flip-flop, the capture flip-flop gets its signal late. This gives extra setup time, but risks a rear-end collision, hurting hold time. Conversely, with negative clock skew, the waveform shows the capture clock triggering earlier. The clock source is wired closer to the capture flip-flop, so the destination opens early. The collision risk is gone, but data has less time to reach the destination, hurting setup time. So the relationship is strictly divided. Positive skew exclusively threatens hold time, while negative skew exclusively threatens setup time. Looking back at our circuit, the listed clock frequency is 2 GHz. By taking the inverse of that frequency, we calculate a baseline clock period, or TC, of 500 picoseconds. To evaluate setup constraints, we trace the longest route. The path begins at the top left flip-flop, runs through 3 XOR gates, and finishes at the destination. With each gate taking 100 picoseconds, multiplying by 3 gives a total longest path delay of 300 picoseconds. Next, we find the shortest path to test hold time constraints. Starting at the bottom left flip-flop, it passes through a single XOR gate. Using the 50 picosecond contamination delay, this fast lane takes exactly 50 picoseconds. These 350 picosecond delays establish the physical boundaries of our circuit. We will use them to find the clock's safety margin. This timing diagram maps out our setup constraint. In the bottom right corner, you can see how negative skew cuts directly into the required setup time window. The goal is to ensure even the slowest data, traveling that longest 300 picosecond route, successfully reaches the capture flip-flop before the timing window closes. Here is the mathematical formula for that relationship. The total clock period, TC, must be greater than or equal to the sum of the flip-flop delay, the maximum path delay, the setup time, minus the clock skew. Let's bring the skew variable over to the left side and plug in our numbers. We have our 500 picosecond clock period, 60 picoseconds for the launch flip-flop, our 300 picosecond maximum path, and the 40 picosecond setup requirement. Adding the circuit delays together leaves us with 400 picoseconds. Subtracting 500 picoseconds from both sides isolates our variable, leaving a final negative boundary of exactly negative 100 picoseconds. This proves the system will remain completely stable even if the destination clock arrives up to 100 picoseconds early. Now we flip to the hold time constraint, shown here on the bottom left of the diagram, where the positive skew interval overlaps with the hold window. We run this equation to ensure data on the 50 picosecond short row doesn't move so fast it overwrites the destination before previous data finishes processing. Our formula states that the contamination delays of both the launch flip-flop and the combinational circuit must be greater than the required hold time plus the skew. We substitute our shortest path metrics, 45 picoseconds for the flip-flop and 50 picoseconds for the single XOR gate, against a 15 picosecond hold requirement. Combining the minimum delays gives 95 picoseconds. Subtracting 15 picoseconds leaves a maximum allowable t-skew of 80 picoseconds. This establishes our upper limit. The destination clock can arrive exactly 80 picoseconds late before the fast-path data overwrites the active signal. Placing both of these mathematically derived limits onto a single timeline visually maps out our safe zone. We are left with a final, conclusive, valid clock skew range. The skew must fall anywhere between negative 100 picoseconds and positive 80 picoseconds. As long as the physical circuit wiring maintains the clock delay inside this exact 180 picosecond window, the 2 GHz processor is guaranteed to operate flawlessly without timing errors.
Thanks for watching. See you next time.